Science on Surfaces.
Welcome to this podcast. Today we will talk about contact angles. We will talk about what a contact angle is, when and why it is important, and how to measure it. Here with me in the studio I have Susanna Lauren, who is an expert on wettability and related phenomena. Susanna has been working at Biolin Scientific around these topics for over 8 years. And before that, she did her Ph.D. on microfluidics and superhydrophobic surfaces, which are very much related to these phenomena. So welcome, Susanna.
Thank you for having me again.
Yeah, it's great to have you here. So let's start with the basics, as always. What is a contact angle?
So a contact angle is a measure of wettability of a surface. So it's maybe easier to understand visually. So you can actually test this at home. So if you take a clean glass surface and you take a plastic surface and you put a drop of water on top. So you can basically see that on a glass surface, the water droplet will spread more than on plastic. So the contact angle is the angle that is formed between the water and the surface. So then since the water spreads more on a glass,
Which is then higher wettability.
Higher wettability and lower contact angle.
Okay.
So and then on plastic, the wettability is not as high, and the contact angle is much higher.
Okay. So what makes the contact angle vary on different surfaces? Why is it different on different?
That's a good question, of course. So contact angle actually arises from the intermolecular interactions between the solid, the liquid, and usually gas. So I mean, it's surrounded by air.
So here you have three different
phases interacting with each other, basically. So then it arises from two different forces. So we have cohesive forces and then we have adhesive forces. So the cohesive forces are the forces that are acting inside the liquid between the similar molecules. So let's say, for example, in water, we have water molecules that are acting, are interacting together. So that's cohesive force. Then we have an adhesive force, which is between the solid and the liquid in this case. So between two dissimilar molecules. So now, depending how strong this cohesive force is inside the liquid, compared to adhesive forces between the liquid and the solid are, then that's kind of it's the balance between these forces that makes the water either spread more on the surface or then kind of bead up at the surface.
So if the adhesive ones are stronger than the cohesive ones, then it will
spread more.
Spread and wet.
Yeah,
them.
wet. Exactly.
And the opposite it will.
Yeah. So I mean, in this case, we were talking about the glass surface and plastic. So the adhesive forces between glass and water are stronger than adhesive forces between plastic and water.
Okay. Is it possible to understand that somehow, or it's just... That's maybe complicated chemistry.
I mean, it is. Yeah, I mean, it's not that complicated chemistry, but I mean, we would need to go into more like divide these forces into different types of interactions.
Okay.
So we would have like polar interactions. So water is a polar liquid. We have hydrogen bonding in water. And then also the glass surface is polar. We have, it's basically silicon dioxide, I mean, if you simplify it a little bit. So we have these polar interactions. So because we have a strong polar interaction in the water molecules, then and the glass is polar surface. So they kind of like each other more.
Okay, I see.
But then the plastic, I mean, in the plastic we have, it's very dispersive. There's no that much like oxygen, for example, in plastics. So then you have this you don't have those polar interactions.
Right.
And that's why you don't get that that spreading of
yeah.
the water on the surface.
Yeah, okay. It makes sense. So why is the contact angle important, or is it important?
Yeah, I mean, of course, it is important. So, I mean, contact angle basically tells how the liquid is interacting with the surface. I mean, it doesn't have to be water. It's just water is kind of an easy example when you talk about these things. But, I mean, it can be any other liquid as well.
Mm-hmm.
And you have maybe heard about terms hydrophilic
Yes.
and hydrophobic before. So, I mean, hydrophilic surface is something that water likes. And usually 90-degree contact angle is used as kind of a threshold point. So if it's below 90 degrees, then you say that the surface is hydrophilic.
Mm-hmm.
And if you have higher contact angle, so above 90 degrees, then it's with water, then it's hydrophobic surface. And then we can go actually a little bit more further if we have really high contact angle. So let's say we have higher than 150-degree contact angle, then we are talking about superhydrophobic surfaces. So, I mean, you have actually touched upon this subject a little bit in your previous episode about hydrophilic and hydrophobic surfaces. So, I mean, for example, hydrophilic surfaces you need in applications like biomedical applications, like in catheters that you talked in one of the episodes. Yeah. And then hydrophobic is, and especially superhydrophobic surfaces are very useful in applications where you want the water to be repelled from the surface. So one really kind of easy example is an outdoor clothing, for example. I mean, you have heard about Coratex. So that's basically a coating that you apply on the coat, on your coat, for example, and that makes the water drops, if it rains, to almost like roll off from your coat, and it doesn't get wet.
Okay, so it's the contact angle is relevant when it comes to interaction with molecules or other materials, or
yes, I mean, of course it is. I mean, it is important also when, I mean, if you think about biomaterial, for example. So if you put that into the body, you first will have water molecules coming on the surface of the biomaterial, and after that you will get proteins and later on cells, for example. So then what this first contact with water is very important because that kind of gives the basis of I mean, what happens after that with the proteins and with the cells.
Yes.
So yes, it's very important, of course.
Okay, so how can you measure it?
So the most typical measurement that you would do is optical tensiometry. So you would have a light source and a camera and basically your substrate in between, and you put just a drop of water basically on top of that substrate. Take the image with the camera, and then the modern softwares are basically able to fit the curve automatically around that droplet and tell you what is the contact angle of that surface. But I mean, in addition to that, there are other methods, and they are mainly for more advanced samples, I would say. I mean, it's relatively easy to measure contact angle on a sheet of plastic, for example. But then if you can even measure contact angles on fibers, for example. And of course, it's not as simple because the fiber can be really, really thin. And then there is no way you can put a droplet on top. I mean, there are methods that you can put a really small droplets on top, but even that can sometimes be too big. So then you can use a method that is based on force tensiometry, where you have a very high sensitive balance, and you actually have that fiber attached to that balance, and then you immerse it in the liquid, and then you pull it up. And by measuring that force, I mean, how much force is needed to immerse it and pull it up, that gives you the the contact angle for that fiber.
Okay, I see.
And we can even measure powders. So I mean, you can imagine that that's also quite a challenge. But there are also holders where you can put powders in, and also by immersing it into the liquid and kind of looking the mass uptake of a liquid, like how fast the mass or the water is penetrating into the powder, gives you an idea of the contact angle of the powder.
I'm thinking the surface of a powder must be very different from a flat surface.
Yes, I mean, absolutely. So that's why you are actually doing it. I mean, there are a few different ways to do it, but I mean, you can do it with the loose powder, so that you have your powder in the container and you have your powder particles there separated, and then you just look how kind of water is absorbed into that powder. But I mean, it's maybe a little bit more niche measurement, and it's a little bit more complicated. I mean, much more complicated than just measuring contact angle optically on a plastic sheet.
Is it possible to explain how the contact angle is related to the absorption rate?
Yes, I mean, it comes from the capillary forces. I mean, it's the same idea. I mean, if you have a really narrow tube and you put it in the glass, you can see that the liquid rises from that tube, and that's dependent on the contact angle of the surface of the tube. So if you have a powder, you basically have like millions of little tubes inside the powder. And that's that. But I mean, it requires quite a complicated mathematics and physics to do the calculations. The softwares that are used are able to do that if you give them enough information to do the calculations.
Okay, but related to the capillary forces.
Yeah, exactly. Yeah.
Okay. So how long does it take then to perform a contact angle measurement?
Yeah, I mean, of course, it varies a lot. I mean, if you think about different type of samples, but if you on a typical example where you have a piece of plastic or a glass plate or something that you measure, I mean, you usually want to measure several droplets on the sample just to get an average contact angle for the whole surface. But even if you do, let's say, 10 measurements in a row, you can actually do quite automated measurements nowadays. And I mean, it's a matter of minutes to do that. But then I think because contact angle has really proven its value in many different applications, so people are looking at it in wanting to do the measurements in more extreme conditions, like at really high temperatures or even under pressure. So you can imagine that that's of course takes much longer time, basically not maybe to measure the contact angle, but the prepare for the measurements. If you have to heat the liquid up, and then even at the pressure.
So basically setting up the measurement, it takes time.
Yeah, and it can be, I mean, it can basically be longer than the actual measurement. The actual measurement can still be minutes, but just to set it up can take time. And of course, those more special samples like powders and fibers, I mean, those can also be, I mean, just because they are, usually you need to maybe repeat them a little bit more, I mean, do repetitions just to be sure that you are actually measuring a correct, I mean, you can average then your measurements, and so that can be a little bit more time consuming, of course.
So anything special that needs to be considered in these measurements?
Yeah, I mean, of course, there are some things like, I mean, one thing is that the contact angle is very sensitive. So it's a very surface sensitive method. So, I mean, it's of course what you want, because you want to be able to detect the changes at the surface.
Yes.
But then at the same time, it can be quite difficult to I mean, if you can have, just by having it on the table, you can get contamination on your surface. And then you can detect it with the contact angle measurement. So this is kind of the reason why it's very difficult to, I mean, we talked about surface tension in the previous episodes. So you can actually look at a literature value for surface tension of water, I mean, of course, it depends on temperature, and it has to be clean water. But I mean, you can look at that value. But then doing the same, I mean, what is the surface tension of what is the contact angle of a glass surface? I mean, water contact angle. That's really difficult to say, because, I mean, is it clean glass surface? If it's cleaned, how is it clean? I mean, have you used some kind of a detergent, for example? And how has it been stored after cleaning? Has it been on a table in a vacuum? And is it, what type of a surface? Is it rough surface? Is it smooth? Is it porous? So all of these kind of make a difference to a contact angle value. So you can't really give any literature value of a water contact angle on a glass. So
you mentioned if you've cleaned it with surfactants or something like that, and I assume then if you have still some surfactants left on the surface, that would have a big impact.
Yes.
And other molecules or contaminations. But what about the roughness, which is something completely different? That's more like a different type of property.
Yeah, it is. But I mean, the wettability is actually dependent both on surface chemistry and surface roughness.
Okay.
So this is actually something that is also kind of used in your favor when you are, for example, making superhydrophobic surfaces, because the surface roughness that you have on the surface will always kind of enhance the chemical property in a way that, I mean, if you have a surface that is hydrophilic in chemistry, so you have below 90-degree contact angle, and then you add roughness to it, you actually decrease the contact angle even more.
Okay.
Or then the other way around. I mean, if you have a hydrophobic surface and then you add roughness to it, you are increasing the contact angle even
How
further.
can this be understood? Is it an easy way to explain that, or?
Well, I mean, it's based on theories that have been, I mean, there is a very famous theory which is Wenzel theory, and it's related to kind of the surface that the droplet sees. I mean, because if you have water, I mean, you think that the surface is smooth, but then in a molecular level, it is not smooth. No. I mean, of course, there are roughness, and the water or whatever liquid you are using is able to penetrate into that roughness. So the actual contact angle of water is basically different than what you are maybe seeing. So, and I mean, this is used in superhydrophobic surfaces because it's actually not even possible to reach 150-degree contact angle with water just by chemistry. So if you would take a Teflon surface, which is like a really, really hydrophobic plastic, you would have 120 maybe, the highest possible contact angle. So to be able to reach that 150 that is needed for superhydrophobic applications, you actually have to do something to your surface. So it can't be just smooth Teflon. So what you do is you add roughness to it. I mean, then there are different types of roughnesses that you can, of course, add. So, I mean, when you really, really want to reach those super high contact angles, you actually have to tailor your roughness so that instead of having the water penetrating into the roughness, it will actually leave little air pockets. So then you get a really high contact angles when you have this. You have that little air pockets in between.
Right. So there are then different ways to tailor the contact angle.
Yes, absolutely. So it's a huge area of research, actually. How do you tailor? I mean, that's maybe already quite well understood, how you tailor those surfaces, but then to make them durable as well. It's because the roughness, I mean, you can imagine that it's quite easy to just break it.
Yeah. So we talked about typical areas where the contact angle matter. You measured biomaterials, clothes, like for cleaning applications. Are there any other typical areas?
I mean, I would say anything where you have adhesion related questions. And I mean, I'm not only talking about adhesion of coating on the surface, but I mean, you can also think about adhesion of cells, for example, as I was mentioning, that if it first you have the water molecules, then you have the proteins, and then you have the cells. So that's adhesion of cells. Yeah. That is important. But I mean, and then there are others like adhesion of crude oil to reservoir rock is something that is very, very much studied with the contact angle. I think, I mean, if we take a simple example, which we could take the coating formulation. So basically, if you have a certain surface that you want to coat, then you have different formulations, A, B, and C, and you want to know which one is best in terms of adhesion. So you could measure contact angle of those formulations on your substrate, and basically the contact angle the formulation that gives the lowest contact angle is the best.
Okay.
But there is a little but because you also want to think about then the surface tension that you have in that formulation. If you have a really low surface tension, so then that means that it would spread actually more on the surface and the contact angle would be lower. But the problem is that if you have a really low surface tension, that is actually, those coating formulations are very prone to foaming, for example. So from a process point of view, they are not anymore very good formulations. So then you basically need to think about, I mean, and also, I mean, how much you have added these additives to your formulation to make the surface tension low. I mean, it's economical thing. I mean, you want to add as little as possible. And then it's environmental thing, you want to add as little as possible to if you have some toxic additives. So actually the best formulation is something that you have as low contact angle as possible with as high surface tension as possible and with as little additives as possible. So it's not that straightforward, but it's
So you have an equation you need to optimize.
Yeah,
basically.
I mean, you are basically optimizing it just by doing different type of measurements and yeah.
Yeah. Okay. So are there any challenges related to these measurements?
Yeah, I mean, the standard measurements are very straightforward. I mean, if you just measure on a sheet of plastic, it's very, very straightforward. But I mean, of course, there was this what we already talked about, the contamination issue. So you want to be always sure what you are measuring, so that you are not measuring basically a different thing just because your sample preparation has been different. So, but then, I mean, for example, if you want to measure these fibers, for example, I mean, you need this very sensitive balance. And your fiber diameter, it can be like under 10 micrometers.
Oh, wow.
So it's really, really small. And you can imagine that if you immerse that into the liquid, the force that it's affected to the balance is really, really small. So then you need, of course, very kind of protected environment so that you don't affect the balance in any other way when you are doing the measurement. Then powders we talked about. I mean, I talked about the method where you immerse it into the liquid. There is actually, I mean, it depends again a little bit on your application, but compressing the powder into tablet is something, a way to go around it a little bit, because then you can actually compress your powder into a tablet and measure contact angle with the optical method on top.
Okay.
So that's kind of a neat way of going around this problem of having this billion of capillaries that you need to try to understand. And I mentioned already the procedures. I think that's extremely important in the oil industry applications where you try to measure the wettability of the rock surface, because you're basically taking the rock from the ground, then you do something to it, you clean it to get the oil out, then everything that you do to that rock it will affect on the contact angle measurement. So to be able to measure those type of, or do those type of studies, we need procedures so that we have two different rocks, but we do exactly the same things to them before we do the measurements. Otherwise, if you try to compare the data, it can be very, very confusing because somebody has done that type of a cleaning and somebody else has used something else. So then, as you mentioned, the residues from cleaning agents, for example, they can be completely different type of surfaces, even though you think that you are just measuring rock.
And is this one of the situations you mentioned where you have those extreme conditions?
Yes, absolutely. So that's when you would like to, in that area, you would want to measure things at the reservoir conditions. So you would like to have high temperatures and high pressures.
Yeah, which is what you have then underground.
Yeah, exactly. Yeah.
Any other challenges? So this is essentially mainly do sample preparation again.
Yes, I would say it's really a sample preparation that you need to consider, and I don't think those procedures are in place yet.
No,
because this area is something that this measurement hasn't been used in that area for so long time.
Oh, okay.
That it's kind of a new thing to this industry.
Yeah.
So then there is still a lot to do to improve those procedures to be sure that you are always measuring what you think you are measuring. But it applies to other things as well. It can be for example, the quality control of your surface. Again, you have to be very sure that you know what you're measuring. So yeah, that's definitely a challenge in a sense, but I think it's easy enough to solve, but you just have to know that's what you need to do. You need to have those procedures in place.
Yeah, exactly. So what about the future of contact angle measurements?
I would see, the contact angle is already utilized in many areas, but I would still see that it will probably expand to new areas. Like I mentioned, that it hasn't been used that much in oil industry yet. So I'm assuming that there are also other areas where you can utilize it much more than you do. And even in quality control, it is used, but it could be actually used much more, because it can see, for example, you could do quality control in terms of cleanliness of your surface, because it is so sensitive method.
Right.
That you can actually see if you have contamination left from the cleaning process, for example. So, I would see that that's one area where it will still increase quite a bit. Then in smart surfaces, we talked about superhydrophobic surfaces, but there can even be oleophobic surfaces. So surfaces that repel oil.
Oh, okay.
So in the same way as superhydrophobic surfaces repel water, now people are kind of moving even to oleophobic surfaces so that they repel oil. And that's, of course, there are a lot of applications where you want this. Then you can talk about like self-cleaning surfaces, or surfaces that the dirt doesn't even stick.
Okay.
So and those,
that would be perfect.
Yeah, exactly. You wouldn't have to clean ever again. But it's that's definitely something that is looked into a lot. And the contact angle measurement is really the only method that's the main measurement that you would use in that sort of a field. And as I already mentioned, the oil, I'm pretty sure that a contact angle will be even more used in oil industry, because it has really been shown that the wettability of the rock surface is very much affecting on the ability to take the oil out from the ground.
Oh, right, yeah.
So you can relate wettability to that. So I would see that will definitely be a growing area for contact angle measurements.
So very important I don't know, property or parameter, or whatever you would call it.
Yeah, in many different application areas.
Yeah,
for sure.
Okay, so I think that's what we had for this episode. So thank you for listening to this episode where we talked about contact angles. So it's been me, Malin Edvardsson, and Susanna Lauren from Biolin Scientific. And I would also like to take the opportunity to mention to those of you who are listening or watching that if you're interested in surface science and related phenomena, you should check out our blog, the Surface Science blog. Thank you.